Okay, I see Zamian, Isabella, and Nevia. So thank you for letting me know you're here. Okay, let's go ahead and get started. First of all, this will probably be one of the last lectures that we will have for my part of the course. The true won't be the same. Sorry, the same will not be true for Mr. Brzezinski. He may have more lectures after this, of course. However, looking at our calendar, we've got today and Friday. So today we're going to have a lecture. Friday we're going to have a quiz. And then the next week we have Monday, which we meet for class. And then Wednesday starts our holiday for Thanksgiving. So no class through the rest of the week. And then after that we have Monday the 30th and Wednesday the 2nd, which will be class days. Now, my plan for us for the rest of the semester is that, again, Friday we will have a quiz, then Monday of next week we will have a lecture, but that would probably be the last lecture we have for this semester. I say that because basically we're at the end and really don't have anything else to teach. But also, I want to give us a good amount of time to prepare for the exam, and part of that is one, I'm going to be giving a review for the exam, And two, I'm gonna want y'all to do as much work as possible on Hawks. So anything you haven't gotten done on Hawks that has been assigned or Mr. Muzinski wants you to do, I want you to get that done before you ever see either of our exams. So preferably you would have everything for Hawks done by the end of Thursday. Okay? Now speaking of exams, I'm looking at our final exam schedule here. And so we meet Monday, Wednesday, Friday at 2, which means that our exam is scheduled for 3 o'clock. Now, I'm probably going to just release the exam at 8 a.m. on Friday. That'd be Friday the 4th. Okay? So usually it's going to be Tuesday, December 8th, but I'm going to probably just give it to us this Friday, December 4th at earliest time because I want us to have a good chance to get it. Hello, Isaac. Okay. And Aileen, good. Good, we have a lot of people in the stream today. Alright, so today I want to switch gears just a little bit. We're still talking about functions today, but we're going to be talking about a new type of function. That is what's called a logarithmic function. First of all, we need to learn what logarithms actually are. You may have heard of them before, probably in high school, and at least for me when I was in high school, they were kind of scary and confusing and something I never really got a good grasp on in high school. But that's probably because my teacher wasn't very familiar with it either. Logarithms are actually very useful tools, and what they allow us to do is look at exponents. And so if we have something like, I don't know, 2 to the x equals 30. What a logarithm will allow us to do is solve for that x. So right now, we know how to do lots of things to solve equations. We can divide things off, add, subtract, whatever we need to do. But what would you do in this case where you have x in an exponent? How do you get an exponent by itself? Well, again, this is where logarithms come in. So before we actually tackle this equation here, I want to show us a few properties of logarithms that we need to know in order to be able to use them effectively. And these are definitely things that you need to write down in your notes. They're definitely things you need to memorize. So, first thing is the product rule. Okay, so the product rule says that if we have a logarithm, which is written log, with a base, so the base is going to be this tiny number written as a subscript. Subscript means that it's down below. Hello, Vicente. So it's going to have a base, and I'll talk more about what this base means in a moment, but it has some kind of base, we'll call it b for now, of x times y. Then this can be rewritten, so it can go both ways. It can be rewritten this way: log base b of x plus log base b of y. Okay, so why does this work? Well, this, again, logs have to do with exponents. And so what do we do with exponents when we're multiplying things with exponents on them? We add those exponents, right? And that's exactly where this comes from. I'm not going to get into the nitty-gritty details of where this actually comes from, where the proof is for it, in other words. But remember that, yeah, when we multiply things that have exponents on them, we're going to add those exponents. Now, like I said, we can write it from this to this, or we can go the other way around. We can go from this to this, where we have, x and y. Well, now we multiply them instead. But that only works if the base is the same. Next rule, quotient rule. Okay? Well, like we said, if we're talking about um, exponents really here, so like the first example, if we multiply things that have exponents, we add those exponents together. What's going to happen if we have something like log base b of x divided by y? So what do we do with the exponents if we're dividing things that have powers on them? Well, if you remember all the way back, I think that was like 3 months ago, we subtract those exponents, and that's exactly what's going to happen here. Is we'll have log base b of x minus log base b of y. So again, this is basically the exact same as the rules that we had for exponents. Continuing with that theme, we have the power rule. So what did we do if we had a power of another power? Okay, let's write that out. So log base b of x to the y. So essentially power to a power. What did we do if we have a power raised to another power? We multiply those two powers together. So same thing here. What's going to happen is this y is going to come out in front to multiply it. So we'll have y times log base b of x. And these are probably the three most important rules. There are more rules, and I will give you those rules, but these are very important to keep in mind. Just like how they were important when we went over them with our exponents. Again, if we have two things that are multiplying, we add their exponents. If we have two things that are dividing, we subtract their exponents. If we have a power to a power, so power to power, then we multiply those together. Okay, so what are we actually talking about with these logs? Where do they come from? Let's say that we have b to the x equals y. Okay, so again, what we have here is an equation, but the number that we're looking for, x, is in an exponent spot. We can rewrite this from what is called exponential form. I'll go ahead and label that. So go from exponential form to what we call logarithmic form. And again, vice versa. So logarithmic form, we will now have log base b. So the thing that we're raising a power to becomes our base. And then the thing that this comes out to be is what we're taking the log of. And it will equal our x. Okay? So this is a way of isolating that exponent, this thing that we're looking for in this exponential equation. We're looking for that x. We can isolate it using a logarithm. So this is a logarithmic form, or log form. Now both of these things say the exact same thing. They have the exact same value. They have the exact same, basically, words in math. It's just that they are different forms of the same thing. So sometimes we will be able to get away with exponential form. Sometimes we need to use the logarithmic form. It just depends on what we're doing and what we're trying to find out. Okay, so going back to our original example, 2 to the x equals 30. Again, something that I want to do here in order to solve for x is to isolate that exponent. I want to get it by itself. So what I can do is I can take the log of both sides, just like we would, add something to both sides to move it over, or maybe divide, whatever. We do things on both sides to try to solve. And I'm going to do the exact same thing here. I am going to take the log of both sides. Okay? So again, I have taken the log of both sides here, just like I would with any other process for solving. Now the thing is, I need to choose a base for my log. The base is the count that is being used. So like, think about like this. So whatever we're raising to a power, maybe this is 3. We know the powers of 3 pretty well, right? We have 3 to the first is 3, 3 to the second is 9, 3 to the third is 27, so on and so forth. So that's the counting system, it's powers of 3. Or like in this case, we have 2. Okay, we're counting by powers of 2. So 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, so on and so forth. So the base of our log is what kind of counting system we're using. And here I'm going to use base 2 because that's what we're talking about. Okay, and this is where another rule comes in. So, if we have, let me go ahead and point it out over here. If we have something like log base b of b to the x, okay? What essentially happens here is these b's will cancel each other out. And this will give us just x. Another way to look at this is that log base b of b is 1. Okay? So what we're really saying here is, okay, counting system, like counting system 2. What would I have to raise 2 to get this? Or what would I have to raise b to get b? Well, you'd have to raise it to the first power. So log base b of b is 1. Log base 2 of 2 is 1. Okay? So we're looking at the power rule here. The power rule says, okay, this power goes out in front. So this x here is going to go out in front because of our power rule. Okay, so power rule tells us, okay, that x is going to go out in front, and then this extra rule, since our base is the same as our number here, that comes out to be 1. Again, how much do you have to raise 2 by to get 2? Well, you only have to raise it to the first power, so that's 1. Well, 1 times x is x, so really our answer comes out to be x equals log base 2 of 30. This is an exact answer. And this is what we are typically going to look for an answer when we're talking about logs. This is going to be useful for us because it is exact, and that helps us do more math later on down the line. If this is the final stop and we need to know like an actual number, we're going to have to plug that into a calculator and see what we get. Okay? Now, most calculators only have one type of base in them. They have base 10 usually. So this base right here is always going to be 10. Well, I don't want to put in 10, I want to put in 2. So how do I get that? I change that base into what the calculator knows. For that we have what's called a change of base formula. Now again, this is the answer that I'm pretty much always going to be looking for. Probably not ever going to want you to use change of base. But the reason I want to show you change of base is so that in the real world, if you ever need to use it, you know how to find it. So the change of base formula says that if you have something like this, like log base 2 of 30, and you want to put into a calculator or just change the base so that you can get something that you can actually use. So let's say log base b of x what we can do is we can choose a base. So like with calculators, base 10. Most calculators use base 10. What this comes out to be is, okay, we can change this into log base 10 and then just put in our x there over log base 10 of whatever our original base was, b. Or this could be any other base. I'm just using 10 because, again, that's what calculators usually use. You could make this base anything. You can make it base 4. You can make it base 7. You can make it base whatever. Okay? It just depends on what type of base you need to be using. Again, I'm using 10 here because that's what calculators typically use. Okay, so let's go ahead and just, for the practice, see what this is as a number, or something we can understand. So I'll go ahead and plug this into my calculator using the change of base formula. So I need to do log, and it's automatically going to give base 10. It automatically does that. Of, let's see, 30 divided by log of, okay, I need my base here, so 2. And see what that gives me, and it comes out to be about, I am going to have to round this because it's a irrational number, 4.90, let's say 7. Okay, so once again, I'm probably going to just want you to use that for your answer because to me that is more useful. It's the one that is more accepted. It's the one that's going to help you do math further on down the line if you need to use this value in something. This is a rounded value. The more and more you use rounded values in your calculations, the further and further off you're going to be from the actual value. Okay, so change of base is good to know in case you use it or in case you need it. But I'm probably just going to want you to give me the exact value. Okay. And of course, if you have any questions, just type them into the chat and I'll get to you. But I'm going to move on to another example. Pretty similar one, basically the same idea. But I want us to have some practice with this. So let's say I have 4 to the x equals, oh, I don't know, 27. Okay. So, let's see. Now I know the powers of 4 pretty well. 4 to the first is 4. 4 to the second is 16. And then 4 to the third is 64. Okay. Well, none of those are right on 27, are they? Obviously. So yeah, we've got another irrational number here. I can't just guess at the x. So I'm going to have to use my rules for logarithms to solve this one. And it's the exact same way that we just did the previous example. I need to take the log of both sides. So I'll take the log of 4 to the x and the log of 27. Okay, so now that we've gotten these, again, it's time for our rules for logs to come into play here. Now we know that due to our power rule, again, power rule here, power rule says that if we have a power in this thing that we're taking the log of, we knock it off and put it on the front. Okay, so let's knock it off, put it on the front. So now we have x times the log of 4 equals the log of 27. Oh, and we forgot to take a base. I do that a lot because it's not really necessary, but I didn't say that. But it's a good idea to have one. In this case, I'm going to choose base 4. Because I know if I choose base 4 here, that if the base matches the number I'm taking the log of, then this will come out to be 1 and basically eliminate this log. And of course, I've got to make that base 4 on this side as well. They have to be the same base. Otherwise, we're not doing the same thing on both sides, and we're throwing our equation off balance. Okay, so this one again basically just becomes 1. And so we don't need it. So we have x equals the log base 4 of 27. Okay? So, again, for the practice, let's go ahead and see what that is in our calculator. We're going to need to use our change of base because, again, calculator doesn't have base 4. So we're going to have to do log of 27, log base in the calculator sense 10 of 27, divided by log base 10 of 4. And we get an answer of about 2.377. And indeed, if I put this into my calculator, 4 to the 2.377, it comes out to be almost 27. So we've gotten this one correct. Any questions at all so far? Okay, again, you can type your questions into the chat. Let's try something a little different. Okay? 9 to the x equals 3. Well, that's odd. How would you raise 9 to something and get 3? Let's take a look at it. Again, using our properties of logs that we've been using so far. So first things first, we're probably going to want to take a log of both sides, right? So I'm going to do log of 9x equals log of 3. Okay. Now that I've gotten this, let's take that x to the other side. I'm sorry, to the front, not the other side. Okay. And I want to do something kind of interesting here. Now, something that I'm noticing about these two numbers, 9 and 3. I know that there's 3 in 9. 9 is 3 squared. So what happens if I rewrite 9 as 3 squared? Well, first things first, that 2 is obviously going to go out to the front with the x, right? So we have 2x times log of 3 equals log of 3. Well, if I choose 3 for my base, then that means that this becomes 1 and this becomes 1. Really? Well, that means that 2x equals 1? Well, then I would have to divide by 2 on both sides to get x by itself, and we get that x equals 1/2. One half. So 9 to the 1/2 power equals 3, which should sound familiar to us. Remember that we can write roots as exponents. Another way of saying that 9 to the 1/2 power equals 3 is to write this exponent not as a rational exponent, but as a root. Remember that we can change rational exponents into roots, into radicals. So the 1 becomes the type of root we have. I'm sorry, the denominator, the 2 becomes the type of root we have, and then the 1 is the power on 9. In other words, this is just the square root of 9 equals 3, which, yeah, that makes a lot of sense, doesn't it? Okay. So yes, there is absolutely a way to raise 9 to a power to get something less than 9. If we want to raise 9 to a power to get 3, we just use 1/2. So this is the power of logs. Logs, again, allow us to take these numbers that are in exponential places and isolate them so that we can solve for them. They can do a lot of other things as well, but this is what we're going to be mostly using them for. Okay. So once again, rules. And I want you to have these written down somewhere. Product rule is the same as our product rule for exponents. If we have log base b of x times y, so we're multiplying two things, well, what do we do if they're exponents, if they're things with exponents on them? We add those exponents together, exactly what we're doing here. Log base b of x plus log base b of y. We just split this up into two logs, one of them being x, one of them being y, and we add them together. Quotient rule, again, think about exponents. When we divide things with exponents on them, what do we do with those exponents? We subtract them. So this becomes log base b of x minus log base b of y. The power rule, so if we are taking a power and raising it to another power, we multiply those powers together. So right here I've got a power raised to another power, basically. And so we multiply this by the log. And the other rule that I wanted to show us, if the base is the same as the number we're taking the log of, then it becomes 1. In other words, you can just cancel these out and left with whatever this exponent is here. A lot of times it's going to be 1 itself. Okay. Now again, let's see, Friday is a quiz. The quiz is going to be pretty simple. The quiz, I want you to be able to take functions and combine them. So do, f plus g, g plus f, which would those be the same thing, right? I want you to be able to do f composed of g. I also want you to be able to show me how this works. Go from exponential form to logarithmic form, or from logarithmic form to exponential form. So remember this framework here. The other thing I'm going to want you to do is solve something simple like this. 2 to the x equals 30. So remember, we use our properties of logs. To solve this, we want to take the log of both sides. It's always a good idea to match that to the number that we're taking the log of. And this is the type of answer I want to see for this. Okay, so that's, again, I want you to be able to combine functions, compose functions. I want you to be able to convert from exponential to logarithmic. And I want you to solve a simple logarithmic equation. All right? But that's all I want you to be able to do on that quiz. It's not going to be a whole lot. Then on Monday, like I said, Monday's the only day that we're meeting next week. So we're going to have another lecture on logs. It's going to be getting into some more of the more complicated details. It's not that difficult though, although I'm not going to go anywhere close to some of the crazy things you can do with logs. But Monday we'll have a lecture, and then I want you to use the rest of our typically scheduled days for the semester to complete Hawks. Do stuff on Hawks, please. Okay? But with that being said, I think that's all we need to cover for today, so I hope you have a great day. I will not see you on Friday. I'm just going to send that quiz out, of course, so won't see you on Friday, and the next time I'll see you is probably on Monday. So have a good day, and I hope you have a great weekend.